Hi friends, let's have a look at problem 1310, exclusive all queries of a subarray. In this video, we're going to do the problem using something similar to partial sums or prefix sums. In between, we're going to use some basic properties of exclusive all. In other words, we're going to use their cancellation properties. So here we are given an array of positive integers. We are also given an array called queries, where each query is a length 2 list. So for each query I, we want to compute the exclusive all of elements from left to right, both inclusive. So we want to return an array answer, where answer I is answer to the S query. So here we have two examples. For the first example, if you compute the first and the second element, so you're going to get 2, right? So let me do a simple computation. So 1, the binary will be 0, 3 will be 1, 1, right? So then you compare the bit positions. So here, in the left, you have 0 and 1, the result is 1. And in the last bit, you have 2 1s, the same, so you get 0. So this is 2, right? So that's the first one. But also you can try others. But the thing is that if you do it each one by one, so you're not going to be very good. So here, what we want to do is to use a exclusive all exclusive all sequence. So basically, we want to, for each index, so we want to compute the exclusive all up to that index. For example, let's call it xi. So basically it's a naught exclusive all up to so ai, right? Then if we have other queries, let's see, if I want to, I have sg, so it's sg, it's a naught up to the ag, then it continue, right? ai up to ag. So here, for demonstration purpose, we are assuming that I is greater than I. Then if you do the query up from g plus 1 to I, right? Then the exclusive all of those elements will be something like si exclusive all with sg, right? The reason is that those are the same, so they are going to cancel and remaining the exclusive all from ai say plus 1 up to ag. So this is the actually the cancellation property. This property actually is induced from the very definition of exclusive all. So the definition or the rule of exclusive all is the following, right? If you have the same bits bits in the position, you're going to get 0. So for example, you have 1 and 1 in the bit position, you're going to get 0. And if you have 0, 0, for sure you get 0. And if you have 1, 0 or 0, 1, so this actually they're commutative, so you're going to get 1. So in other words, if a bit position have the same bits, so you get 0. Different, you get 1. So if this actually induced, if you have same number, say n, and then you exclude it with itself, you are going to get 0. The reason is that because it's the same they are the same number, their binary representation are the same for sure. For each bit position, their bit numbers are the same, so you're going to result 0 according to this rule. So this is what we use here. So with that said, actually we are ready to write the code. So let me first I'm going to get the length of this array. Let's call it n. This is just for convenience. So I want to make a partial exclusive all sequence So we can choose to modify this array argument directly or in place, but we try. Maybe it's good practice to avoid that. So let's do something like this. This sequence, I'm going to make a copy of this array, and then we make this sequence. So this is very straightforward. So that's for I in range 1 to n, right? So we do exclusive all exclusive with the previous ones, right? Because the previous ones is up to I-1 element, and then if you exclusive with the current element in the ith position with the previous ones, you are going to get the result for each will be something like this. XOR I will be the exclusive alls for all those elements. So A naught up to a I, right? So this actually we're done. So now let's do the queries. I'm going to use this part, right? So what we want to do is for ij, this is a tuple in queries. So we want to compute from I to j, both inclusive. So we need to do exclusive all from I-1, then XORs j. But you know, this I in the query can be 0, right? That's what we want to notice. So you cannot write -1. The -1 will be the last element in this list. So what? But if it's 0, actually it's just starting from the beginning. So we are going to check if I equals 0. So what we want to do is let's initialize a result variable. So to hold the result, so I'm going to result append. So we just need to do up to j, right? From 0 to j. Otherwise, what we do is the following. So result append. So the reason we write this is I-1 because I is not 0. So I-1 is greater than or equal to 0. So in other words, we are always counting from the left without using negative indices, right? So that's basically about it. So we can return the result state. So if you let's first do a test. It passes the first example. Now let's look at the generic case. It passes the generic case. So let's look at the term complexity, right? So here when we do this, so basically it's O of n, right? And then if we do this, it's O of m, where m is the length of the queries. So overall, it's O of n plus on plus om, right? So basically linear. So that's basically one example of using exclusive OR. So actually, if you practice more for lead code problem, you can find that there are many problems you can use or utilize the exclusive OR idea to address the questions. So yeah, so here we provide one format of solutions. So with that said, I guess that's it for the current video.